welcome to lecture series on advanced linear algebra. Today I will talk about the eigenvalue and eigenvector of diagonalizable linear operator. Already I have defined what is the meaning of or the definition of diagonalizable linear operator. So, if I consider T be a diagonalizable operator on a finite dimensional vector space V over the field capital F, and let B equal to alpha 1, alpha 2, alpha n when order basis consist of eigenvectors of T, and say C1, C2, Cn be the corresponding eigenvalue, then the matrix representation of T with respect to B is equal to a diagonal matrix like this, whose diagonal entries are C1, C2, Cn like that. All other entries are 0. So, this means that if I consider any other order basis on vector space V, then T will also have a matrix representation with respect to that also. So, I can say that the matrix will be similar to this diagonal matrix. Indirectly, I will say that the matrix representation of T with respect to this order basis is basically a diagonal matrix. Okay, fine. Again, it may happen that C1, C2, Cn all are not distinct. Suppose C1 repeated D1 times, and similarly other eigenvectors. There are suppose k distinct eigenvalues C1, C2, Ck, where the 1 is with the top suffix like this C1, C2, Ck, and then maybe I can define the Cj equal to Ci, I equal to 1 plus sigma ds, s equal to 1 to j minus 1 to sigma ds, s equal to 1 to j. What I mean to say you that C1, that is basically I will say that suppose C1, C2, CD1, up to that this is this one, when because all are same eigenvalue page. Then similarly C2 also defined, say CD1 plus 1 to CD1 plus D2. Similarly C3, Ck please. So, if this is the case, then the matrix representation of T, this diagonal matrix, this what I have written here, can be again rewrite like this. This I am basically writing some sort of block diagonal matrix type. Again in this block, this matrix is again a diagonal matrix with the entries are here C1, C1, C1 like that, then C2, 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 it will be, this is basically D1, first one is D1 into D1 matrix, second is D2 into D2 matrix, and last one dk into dk. So, that your sigma di I equal to 1 to k equal to n. So, this is basically rewritten the matrix representation of T when some roots are repeated please. So, in this case if you want to calculate the characteristic polynomial. So, in this case, so the characteristic polynomial will be what? So, suppose if I write this is equal to say capital D, then so the characteristic polynomial of D will be determinant of D minus xi, this one. So, D minus xi means this is basically C1 minus x, C1 minus x like that. So, this means it will have x minus C1 power, it will be D1 into x minus C2 power D2 and so on x minus Ck power dk type. So, this is suppose this is the basically characteristic polynomial effects of this linear operator T. Interestingly, if I want to see the null space, so then the null space of D minus suppose C1 I. So, this is equal to, this will basically again a diagonal matrix, it will be again a diagonal matrix. The first block matrix, that is of D1 cross D1, all entries will be diagonal entries be equal to 0, but second, third up to kth one block matrix, the diagonal entry will be C2 minus C1, all the elements for second block element will be C2 minus C1, and for last one Ck minus C1. Since C1, C2, Ck are distinct, so their difference is also non-zero. As a result, if I want to know that the null space of D minus C1 I, then this is basically is the solution of solution space of D minus C1 I into capital X equal to 0. So, certainly I am getting, because all except the first D1, if we consider capital X equal to x1, x2, say xn, then this x1, x2, xn is basically like that, I will have only D1 number of free variables. Apart from D1, all other variables xi will be equal to 0, because I am getting straight away the expressions from the D minus C I x. If I write this equation, I am getting all the value of xi equal to 0 except first D1 entries, please. So, x1 to xd1 I am not saying anything, but apart from xd1 plus 1 to xn all will be 0. So, this implies I am getting exactly D1 number of free variables in the solution of D minus C1 I x equal to 0. This implies if W1 is the solution space of D minus C1 I x equal to 0, then the dimension of W1 will be number of free variables, that is exactly D1, where all other entries are 0. Similarly, the dimension of null space of D minus C I this x equal to 0 will be D I. So, that is I am getting from the definition of the diagonalizability of the operator T, please. Fine. Now, we are curious to know, is there any relation between V over which the operator is defined and eigenspaces W1, W2, Wk. A null space of D minus Cii is basically eigenspace of the eigenvalue Ci. Eigenvalue is related to the, eigenspace related to the eigenvalue Ci, please. So, this is the question, is there any relation between V and eigenspaces W1, W2, Wk? This is the question, please. Before going to answer these questions, let us talk about some standard results. So, let me write one result in terms of lemma 1 like this. Let T be a linear operator on a vector space V over F. Let C be an eigenvalue. Eigenvalue of T and alpha be a corresponding eigenvector, that is T alpha equal to C alpha. Then for any polynomial function f x over capital F, f of t operating on alpha will be equal to f c alpha. This is very simple results. If C is an eigenvalue of the operator t, alpha is the corresponding eigenvector, that is T alpha equals C alpha, then for any polynomial function f x over the field capital F, f t operating on alpha must be equal to f c into alpha. Proof is very straightforward. Let f of x the polynomial function, who let me consider this is equal to a naught plus a 1 x plus a 2 x square plus a n x to the power n, where a I are from the set capital F I equal to 0 to n. So, this is equal to, I can rewrite very simple notations, that is a to the power I into x to the power I equal to 0 to n. So, f of t will be equal to, I can write down your a to the power I and t to the power I equal to 0 to n. T to the power 0 equal to basically identity operator, identity function or identity operator. So, this implies f of t operating on alpha will be sigma a I and t to the power I equal to 0 to n, this operating on alpha, which is equal to, one can write down sigma a I and t I power alpha. Okay, this one I equal to 0 to n. So, this is nothing, we are writing a naught into I plus a 1 into t plus a 2 into t square plus a n t to the power n operating on alpha. So, this means that I will have a naught into I alpha plus a 1 into t alpha plus a 2 into t square operating on alpha plus a n t to the power n operating on alpha. So, this is equal to a naught into alpha, because identity map alpha to alpha itself, plus this will be a 1, since t alpha equal to c alpha. So, it will be c times your alpha. T square operating on alpha will be equal to how much? T square of alpha equal to t of t alpha. So, this is equal to t of c alpha, which is equal to c into t of alpha, which is equal to c into c alpha. So, this is equal to c square alpha. So, t square operating on alpha give me c square alpha. Similarly, we can have t to the power r operating on alpha, I will have c to the power r alpha, please. So, this means that I will have here a 2 and c square alpha plus a n c to the power n and alpha. So, this means that we are getting your a naught plus a 1 into c plus a 2 c square plus a n c to the power n into alpha. This is nothing f of c into alpha, please. So, f of t operating on alpha gives me f of c into alpha, please. Okay, fine. Now, with this help of these results, we are going to prove a nice results. So, it is like this. This is another lemma. I can say lemma 2. Let T be a linear operator on a finite dimensional vector space V over the field capital F. Let C1, C2, Ck be the only distinct eigenvalues of T. Let Wi be the eigenspace associated to eigenvalue Ci, and this is for I equal to 1 to say k. Since V is a finite dimensional vector space, is Wi will be also finite dimensionals. Okay. Let W is equal to sum of subspaces W1, W2, Wk, W1 plus W2 plus Wk. Then dimension of W equal to sigma dimension of Wi I equal to 1 to k. In fact, if B1, B2, Bk be the order basis of W1, W2, Wk respectively, then B equal to B1, B2 and Bk will be an order basis of W, please. So, this is the small results. So, let us try to give the proof of this result, please. Okay. So, given W equal to W1 plus W2 plus Wk. Since each of Wi is finite dimensional, so W has to be finite dimensionals. There is no question or doubt, please. Okay. And W1, W2, Wk are the eigenspaces associated to eigenvalues C1, C2, Ck respectively. Now, by showing that dimension of W equal to dimension of W1 plus dimension of W2 plus dimension of Wk, we are basically showing that eigenspaces associated to distinct eigenvalues are linearly independent. Apparently, we will see that dimension of W will be less than dimension of W1 plus dimension of W2 plus dimension of Wk, because maybe some vectors vectors of W I equal to 1 to k are related. So, I mean to say they are linearly dependent, they are interrelated type. So, in that case, and since the W is basically sum of W1 plus Wk, so certainly the dimension of W is expected that will be less than or equal to dimension of the each Wi, please, sum of the okay, this one dimension of the W1 plus dimension of W2 plus dimension of Wk. On the basis of the hypothesis that eigenvectors of Wi may be related to the eigenvectors of the Wj, I mean vector of the Wj, please. But our claim is that it is not less than, it will be exactly equal to basically, I mean dimension of W will be equal to dimension of W1 plus dimension of W2 plus dimension of Wk. This is our claim, please. But our claim is dimension of W equal to dimension of Wi I equal to 1 to k. Okay, so to do this, what I will do, we will proceed as below. So, we have we shall show that if W equal to say beta 1 plus beta 2 plus beta k, where beta I belongs to Wi and W equal to 0 will imply beta I equal to 0 for I equal to 1 to k. We want to show this one, please. So, first I will show this one, please, that if the sum of this element, the W equal to 0 mean each of the beta I equal to 0, that I have to show first. Then we will go for the next step, please. So, let 0 equal to beta 1 plus beta 2 plus beta k. Let f x be any polynomial function on capital F. Then f of t operating on 0 equal to 0 equal to f of t operating on beta 1 plus f of t operating on beta 2 plus f of t operating on beta k. So, as per previous results, I mean previous lemma, f of t beta 1, beta 1 is an eigenvector associated to eigenvalue C1. So, this will be f of C1 beta 1 plus f of C2 beta 2 plus f of Ck beta k. So, we have 0 equal to this quantity, and this is true for any polynomials. So, in particular a polynomial f I x such that f I C j equal to delta I j. I mean to say, suppose this polynomial is a polynomial of degree n. So, when one can consider Lagrange interpolant polynomial of degree n, and we can have this type of criteria satisfied, f I C j equal to delta I j. In this case, we have f I t operating on 0 equal to 0 equal to I will have Fi C1 beta 1 plus Fi C2 beta 2 plus Fi Ck beta k. Since Fi Cj equal to delta Ij, which is equal to 0 for I not equal to j, 1 for I equal to j. This implies 0 equal to beta I. So, this is true. See, this I have taken polynomial Fi, here I can say I equal to 1 to k. You can take F1, F2, F3, Fk, and applying each of them we will see that beta 1 equal to 0, beta 2 equal to 0 and beta I equal to 0 please. So, this implies that beta 1 plus beta 2 plus beta k equal to 0 implies beta I equal to 0 for I equal to 1 to k. Let dimension of Wj is dj for j equal to 1 to k. So, let Bj order basis, this is consisting of I can say okay. So, let me consider the order basis Bj for the Wj, Bj is equal to alpha I plus 1, alpha I plus 2 to alpha I plus dj, where I equal to basically sigma ds, s equal to 1 to j minus 1. So, I have B1, B2, Bk, they are the order basis for W1, W2, Wk. Now, claim B consisting of all the B1, B2, Bk, which is basically I will have alpha 1, alpha 2, say alpha n be a linearly independent set please. Suppose not, then we have something like W1 plus W2 plus Wk equal to 0, where Wi is linear combination of basis element of Wi. Now, if W1, W2, Wk equal to 0, according to our last results, we have Wi equal to 0 for I equal to 1 to k. So, this implies that Wi which is equal to sigma, I can say that it will be equal to sigma kj into alpha j. So, if you are talking about the I, then it will be your j equal to some number t to say t plus di, t to t plus di, where t is equal to I will have sigma ds s equal to 1 to I minus 1. Okay. So, this one like this thing. So, this implies that since they are all linearly independent elements, therefore, all the coefficient has to be equal to 0. Since alpha j belongs to B I, so linearly independent, as a result implies all kj equal to 0. So, this implies that B consisting of B1, B2, Bk will be a basis of W. So, this implies dimension of W equal to sigma dimension of Wi I equal to 1 to k. Now, I shall utilize and summarize the definition of diagonalizability of the operator. So, if T is diagonalizable, then we have V equal to W1 plus W2 plus Wk, f of x equal to x minus c1 power d1, x minus c2 power d2 and x minus ck power dk, please. Okay, characteristic polynomial this one, please. So, this is all about this diagonalizability of the operator, please. So, we see that if T is diagonalizable, then T can be written as a sum of subspaces W1, W2, Wk, where Wi are the eigenspaces associated to the eigenvalues C1, C2, Ck. And the characteristic polynomial is f x equal to x minus c1 power d1, x minus c2 power d2 and x minus ck power dk. We can cross check these results by considering our previous examples, what I considered a matrix that A equal to now based on this we see, if we recall our last example where A equal to 5 minus 6 minus 6 minus 1 4 2 and 3 minus 6 minus 4, we have corresponding characteristic polynomial is like f x equal to f x minus 1 into x minus 2 whole square, and so we have two distinct eigenvalues 1 and 2. So, the eigenspaces associated to the eigenvalue 1 is W1, that is basically linear span of 3 minus 1 3 transpose, and W2 is the eigenspace associated to eigenvalue 2, we have 2 1 0 transpose and 2 0 1 transpose. So, linear span of these two linearly independent vectors will give me the eigenspace W2, and you will see that your V is equal to when the space of all 3 tuples, that is F3 cross 1 equal to basically W1 plus W2. Of course, we have a non-singular matrix P such that AP equal to PD, where the P consists of the eigenvectors only, that is first column is eigenvector associated to eigenvalue 1 and other two columns are eigenvector associated to 2 only. And so, we see that AP equal to PD. So, this implies that A is similar to D, that is I have A equal to PD P inverse. That is basically the beauty of a diagonalizable operator please or matrix. We will continue in next class please. Thank you.